Salam, peace be upon you. My name is Muhammad Layak Siddiqui, the father of all of us. Part 57, Falsifiability as Courage in Phi Pattern Claims. We began with pattern itself, what can be compared, what stays the same through change. The fourfold identity gave us the bones. A pattern is itself across transformations, and we can prove it publicly. We learned to measure without smuggling time, to remember without storing the past, to model without confusing map and territory. Part 51 built the firewall between layers. Part 51.5 protected the past from future rewriting. Part 52 reframed error as diagnostic signal. Part 53 taught us to correct while preserving lineage. Part 53.5 gave us a taxonomy of failure. Part 54 taught us that uncertainty is the shape of finite access. Part 54.3 distinguished kinds of not knowing. Part 54.5 showed us that instruments drift and must be calibrated. Part 55 taught us that claims must be replayable. Part 56 taught us that paths must be auditable. Now we face the ultimate test. Is the claim willing to risk being wrong? The problem we now face, the claim that cannot fail. Imagine someone makes a claim that seems impressive at first. They say, there is a hidden force that influences all events. It is invisible, undetectable by any instrument, and leaves no trace. But it is real, and it shapes everything. We ask, how would we know if this force doesn't exist? They answer, you can't, it's hidden, but that doesn't mean it's not real. We ask, what evidence would convince you that you're wrong? They answer, nothing, I know it's true. Now, is this a scientific claim? No, it is something else. It is a belief, a doctrine, a story, but not science. Why? Because it cannot fail. It is protected from reality. No possible observation, no possible measurement, no possible evidence could ever count against it. This is the problem of falsifiability. A claim that cannot be proven wrong is not a scientific claim. It may be meaningful in other ways, as poetry, as faith, as personal conviction, but it cannot enter the space of public pattern science. Why? Because science is about testing claims against reality. If a claim is structured so that no test could ever count against it, then it is not testable. And if it is not testable, it cannot be part of public science. Falsifiability is the courage to say, here is what would show I am wrong. Without that courage, a claim remains private narrative. It may be persuasive, it may be comforting, it may be deeply felt, but it is not science. What falsifiability really is. Falsifiability is often misunderstood. People think it means a claim must be proven false, or a claim must be capable of being definitively disproven. But in pattern science, falsifiability is more precise and more practical. Falsifiability means that a serious Phi pattern claim must declare what observable or operational outcome would show that the claimed pattern structure does not hold within scope. It is not about proving the claim false. It is about specifying what would count against it. Think of it like a bet. If we make a bet, we specify the conditions under which we win and the conditions under which we lose. If we never specify the losing conditions, it's not a real bet, it's just talk. A scientific claim is like a bet with reality. It says, here is what I believe about the pattern, and here is what would have to happen for me to accept that I'm wrong. That is falsifiability. A simple everyday example, the weather forecast. Imagine a weather forecaster says, it might rain tomorrow. If it rains, they were right. If it doesn't rain, they were still right, because they only said might. This is not falsifiable. No outcome counts against it. Now imagine a different forecaster says, tomorrow at noon, at the city center, there will be measurable rainfall of at least 1 millimeter. If noon comes and the city center is dry, the claim is falsified. If it rains exactly as predicted, the claim is strengthened, not proven absolutely, but supported. The second forecaster has taken a risk. They have specified conditions under which they would be wrong. That is falsifiability. The first forecaster has taken no risk. Their claim is protected from reality. It may be true in some loose sense, but it is not scientifically useful. Why always true somehow claims are not scientific? There is a whole class of claims that are structured to be always true somehow, somewhere, under some interpretation. These claims are protected from falsification by their own flexibility. Consider, everything happens for a reason. If something good happens, it was meant to be. If something bad happens, it was also meant to be. There is no event that can count against this claim. It is always true, but only because it has been made unfalsifiable. Or, the universe is fundamentally good. If we see kindness, that's evidence. If we see cruelty, that's also evidence. Perhaps a test, perhaps a mystery. No possible observation can falsify it. These may be meaningful as personal philosophies or religious beliefs, but they are not scientific claims. They cannot be tested. They cannot fail. And because they cannot fail, they cannot teach us anything new. Science requires the courage to be wrong. If a claim cannot be wrong, it cannot be science. The falsifier as declared failure condition. In pattern science, we give a name to the thing that would count against a claim. We call it a falsifier. A falsifier is a declared failure condition within scope. It says, if this happens under these conditions with these tolerances, then my claim is not supported. A good falsifier is specific. It is not vague. It is not something might go wrong. It is if we measure X and get value Y outside this range, using this instrument under these conditions, then the claim fails. A falsifier is tied to the claim's window. It respects the boundaries of the claim. It acknowledges uncertainty. It specifies tolerances. And crucially, a falsifier is declared in advance, not after the fact. It is not invented to explain away a failed prediction. It is part of the claim from the beginning. An example across scales. Let us see falsifiability at work across different scales of reality. At the quantum scale, a physicist claims this particle has a half-life of 1.2 microseconds. A falsifier would be if we measure 1,000 decay events with a calibrated detector and the mean half-life is outside 1.1 to 1.3 microseconds, then the claim is falsified. At the biological scale, a biologist claims this gene is essential for cell division in this organism. A falsifier would be if we knock out the gene using standard CRISPR protocol in 100 independent trials, and cell division proceeds normally in at least 90% of cases, then the claim is falsified. At the medical scale, a doctor claims this drug reduces blood pressure by at least 10 points on average. A falsifier would be in a double-blind, randomized trial with 500 patients, if the mean reduction is less than 5 points with p 0.05, then the claim is falsified. At the climate scale, a climate model claims global average temperature will increase by 2 to 3 degrees Celsius by 2100 under this emissions scenario. A falsifier would be if by 2050 the observed temperature is outside the model's predicted range by more than twice the model's uncertainty, then the scenario-specific projection is falsified. At the personal scale, a friend claims, "I will always be there for you." Is this falsifiable? What would count against it? If they miss one call? If they are unavailable during a crisis? The claim is so broad that it's hard to specify a falsifier. That doesn't make it meaningless. It makes it a different kind of claim, one based on trust and relationship rather than testable prediction. 7. The falsifier must be tied to the window. A falsifier cannot float free. It must be tied to the claim's window. The window includes the conditions under which the claim holds, the transformations that are relevant, the invariance expectations, the tolerances for deviation, the uncertainty bounds that apply. If the falsifier ignores these, it's not a fair test. For example, if a claim is about behavior at room temperature, a falsifier that tests it at freezing temperatures is not relevant. The claim never claimed to hold there. If a claim has declared uncertainty of plus or minus 5%, a falsifier that requires exact match is not fair. The claim never claimed exact precision. A proper falsifier respects the claim's own declared limits. 8. Failed falsifier attempt strengthens the claim. Here is the crucial point. When a falsifier is tested and the claim survives, the claim is strengthened, not proven absolutely, not confirmed beyond doubt, but strengthened within scope. Think of it like a rope. Each failed attempt to break it gives us more confidence that it will hold. But we never know for certain that the next pull won't snap it. Scientific claims are the same. Each time they survive a genuine attempt at falsification, our confidence grows. But they remain open to future testing. They are never proved in some final, absolute sense. This is why falsifiability is so important. It creates the conditions for learning. When a claim survives testing, we learn that it has some robustness. When a claim fails testing, we learn that it needs revision or rejection. Either way, we learn. Claims that cannot be tested teach us nothing. 9. The principle of testability priority. This leads to a foundational principle. The meaningfulness of a Phi pattern claim is bounded by its testability. Claims that cannot, in principle, be tested against pattern reality may be interesting narratives, but they are not yet pattern science. In simpler form, if you can't test it, it's not science. Or even shorter, testability first. This principle does not dismiss other forms of human meaning. Poetry, faith, philosophy, art, these are valuable, but they are not science. Science requires testability. It requires the courage to specify what would count against a claim. A claim without a falsifier remains private. It may be personally meaningful, it may be culturally significant, but it cannot enter the public testing space. It is shielded from reality. 10. An analogy. The unbreakable vase. Imagine someone claims to have an unbreakable vase. We ask, "How do you know it's unbreakable?" They say, "I just know, it's special." We ask, "What would happen if I dropped it on concrete?" They say, "Well, don't do that. That's not a fair test." We ask, "What would count as a fair test?" They say, "Nothing. It's unbreakable, so no test could prove otherwise. If it breaks, it wasn't really unbreakable." This is not a claim about a vase. It's a claim about a concept that has been protected from reality. The vase may be real, but the claim about it is unfalsifiable. Now imagine someone else says, "I have a vase that I believe will survive a drop from 1 meter onto carpet. If it breaks, I'll accept that I was wrong." This is a falsifiable claim. We can test it, we can learn from it. The difference is the courage to specify failure conditions. Another analogy, the unseen gardener. Philosopher Antony Flew once used an analogy about two explorers who find a clearing in a jungle. It's well tended, flowers, weeds removed. One explorer says there must be a gardener. The other doubts. They set up watch. No gardener appears. The first says, the gardener is invisible. They set up motion sensors. No detection. The first says, the gardener is intangible. They set up scent detectors. Nothing. The first says, the gardener has no odor. At each step, the claim is revised to escape falsification. Eventually, the claim becomes, there is a gardener who is invisible, intangible, odorless, undetectable by any means, and who never leaves any trace. At this point, what is the difference between this claim and the claim that there is no gardener? There is no testable difference. The claim has been protected from reality. This is the problem of unfalsifiability. When a claim is adjusted to escape every possible counter-evidence, it ceases to be a scientific claim. Falsifiability and claim types. Different kinds of claims have different falsifiability conditions. Identity claims might be falsified by showing that the supposed pattern is not invariant under declared transformations. Predictive claims might be falsified by showing that outcomes fall outside declared uncertainty bounds. Causal claims might be falsified by showing that interventions do not produce expected effects. Interpretive claims might be falsified by showing that the mapping from pattern to meaning is inconsistent or unmotivated. The form of the falsifier depends on the claim type, but the requirement is universal. There must be some specifiable outcome that would count against the claim. The falsifiability principle. Let us state the principle clearly. Falsifiability is how Phi Pattern claims remain accountable to pattern reality rather than protected by rhetoric. A claim without a falsifier is not yet public science. In simpler form, specify what would count against you or your claim is not science. Or even shorter, risk being wrong or you're not in the game. This principle is foundational because it separates science from other forms of discourse. It is not about being right, it is about being willing to be wrong. What a falsifier must include. A proper falsifier declaration must include the falsifier condition itself. What specific outcome would count against the claim? The measurement or trace needed to test it. What would we need to observe? The scope of the falsifier. Under what conditions does this test apply? The tolerances and uncertainty bounds. How much deviation is allowed before we consider the claim falsified? What counts as pass-fail? Clear criteria for interpretation. This is not bureaucracy. This is the architecture of accountability. The falsifiability gate. Because falsifiability is so central, it needs its own gate. Gate, falsifiability declaration. Any public claim must declare where material, falsifier condition. What would count against the claim? Measurement requirements. What evidence would be needed? Scope of falsifier. Under what conditions does the test apply? Tolerances and uncertainty bounds. How much deviation is allowed? Pass-fail criteria. How will we interpret the outcome? This gate ensures that claims are not shielded from reality. What we refuse. With falsifiability as a core requirement, we have clear grounds for refusal. We refuse any claim that lacks a falsifier, has a falsifier untethered from scope, uses moving goalposts to escape falsification, is presented as unfalsifiable truth, has no testability in principle, rescues itself by shifting meaning after the fact, treats failed falsification as absolute proof. Each refusal protects the integrity of public science. Falsifiability as courage. There is something deeply human about falsifiability. It takes courage to specify how you could be wrong. It means admitting that you are not infallible. It means opening yourself to the possibility of failure. It means risking that your cherished idea might not survive contact with reality. But this courage is precisely what makes science possible. A person who hides behind unfalsifiable claims is not protecting their ideas. They are protecting themselves from learning. They are choosing comfort over truth. A person who declares falsifiers is saying, I am willing to be wrong. I am willing to learn. I am willing to let reality have the final word. That is scientific courage. With falsifiability established, we have the tools to ensure that claims are testable, that they risk contact with reality, that they specify what would count against them. But science is not done by individuals alone. It is done by communities. And communities sometimes disagree. Two scientists can look at the same evidence and reach different conclusions. Two labs can run the same experiment and get different results. Two interpreters can read the same text and find different meanings. What then? How do we handle disagreement without descending into chaos or authority? That is where we go next. Disagreement will give us the tools to understand, analyze, and resolve disagreements in a way that strengthens rather than weakens science. Because disagreement is not failure. Disagreement is data. It tells us where our understanding is incomplete, where our methods are inconsistent, where our interpretations diverge. The question is not whether we disagree. The question is what we do with it. We have added another layer to our growing science. We learned that falsifiability is not about proving claims false, but about specifying what would count against them. We learned that always true somehow claims are not scientific. They are protected from reality. We learned that a falsifier is a declared failure condition within a scope, tied to the window, the transformations, the invariants, the tolerances, the uncertainty. We learned that failed falsifier attempts strengthen a claim within a scope, not absolutely, but incrementally. We learned that a claim without a falsifier remains private. It may be meaningful, but it is not public science. We learned that falsifiability is courage, the courage to risk being wrong, to let reality have the final word. A science without falsifiability is a science without learning. A science with falsifiability is alive. We are building a living science. Now we go deeper still, into disagreement, the space where different observers meet and where science is tested not just by reality, but by each other. Because a science that cannot handle disagreement is fragile. A science that learns from disagreement is strong. Always, peace be upon you.